Great. So today we will briefly reintroduce system dynamics modeling and agent-based modeling and do a little bit of a primer on the motivations behind NetLogo and a little bit of additional NetLogo help for those working on the lab for this week, which will be a lab that is focused on agent-based modeling, another type of simulation. And you will have an opportunity to use this one particular program, NetLogo, in order to do some of that agent-based modeling or work with agent-based models. But before we get there, since we just did a lab that was based on another important type of simulation, Monte Carlo simulation, I just wanted to have a couple, give a couple quick notes about that lab now that everybody has gone through it and has seen it. Out of curiosity, so I'm just kind of looking at the participants list here, and so it'd be a good thing to vote in the participants list. How many people have had experience with Monte Carlo trials or Monte Carlo simulations or Monte Carlo runs in the past? Say some previous class or projects you worked on, internships, things like that. How many people are already familiar with Monte Carlo runs before this? Anybody? How many people were not? So now if you vote if you were not familiar with Monte Carlo sampling before this. All right, I see one. Okay. Great, okay, all right. So this is gonna be, looks like we're getting kind of a sample here, that this is a sort of a first experience for some of you in this particular. So even outside of those of you working, so in this class is focused on these dynamical simulations, and you really should know about these for reasons that I'll motivate here when we get back to the main lecture. But there'll be a bunch of you who won't need to use simulation in your everyday life, but even those of you who aren't using, say, dynamical simulations like discrete event system simulations, my guess is that you will periodically have to make use of Monte Carlo sampling. It's just super useful and is used in such a wide variety of different contexts. And I see, I'll assume that so I'm going to hit clear all, and I'll assume that all the hands that were raised there were just hands answering my original question. But if you do have a question, feel free to raise your hand or put a question in the chat or something like that. That'd be great. All right, so and as an example of that, in the lab, I had you do two things that were very different. And so one of them was a very weird thing, estimating pi. And it turns out that this way of estimating pi, by effectively throwing random, so originally those Buffon's needle experiment was you threw random, needles, you sprinkled them onto boards, like boards of like a lunch table or something like that, and you just happen to count up how many straddled the lines between the boards, and you could, by counting all those things up, you could actually get an estimate of pi. And so there's a weird power in randomness that you can estimate something like pi, which normally you think of as, well, it's like, well, I've got to take a circle and I've got to measure its circumference and measure its diameter super precisely, and maybe I take divide one by the other, or maybe I've got trigonometry methods where I take a Taylor series expansion, and if the expansion's long enough, then I can, there are all sorts of ways you could estimate pi that in some ways to me make sense, but just like throwing a bunch of random marbles down and counting just doesn't seem like that should be a way to estimate pi. But it turns out that you can. And so, and the basic motivation comes from this idea that if you had a square and you inscribed a circle in it, then we have to ask, well, what's the fraction of the points that fall within the circle if they're just dropped on the square? And if you think about that, well, the probability that they land in the circle is just the area of the circle divided by the total area, the area of the square. And if we know that the square has a diameter, or the square has a total length on its leg here of 2r, then its area is 2r squared. And we know that the formula for the area of a circle is pi r squared. And it is that formula for area that gives us access to pi through randomness. And so we know that the probability of hitting the circle when you drop things on the square is going to be equal to pi over 4. So if you drop enough things on this, and you count up how many actually land within the circle. So you have to have a way of defining what it means to land within the circle. But if you have a way of counting those things up, then if you have enough of them, then that becomes an estimate of pi over 4. And if it becomes an estimate of pi over 4, it thus becomes an estimate of pi, because you just multiply it by 4. So it's just extremely elegant. You just, if you drop enough random things, as long as you know how to generate random things, that's the key. That's the hard part, is that I need to somehow be able to uniformly drop things over this square. But once I can do that, there's so many powerful things I can do just by accessing formulas that have to do with geometric areas. And that's what we did here. And so, with that in mind, we didn't even have to use the whole square. So in that lab, we just used a corner of the square. And so in the corner of the square, you can say, well, what's the area of the corner of the square? Well, that's maybe just r squared. And then what's the area of that little section of the circle? And that's pi r squared over 4. And I get the same thing. So it kind of makes sense that if there's a pi over 4 probability of hitting the circle in the whole square, there's also a pi over 4 probability of hitting the circle in this little section here, this little quadrant here. And so again, you just, as long as you have a way to drop marbles on this square and then have a way to count how many marbles land within the circle, then you have a way to estimate pi. And that's what you did in the first part of the lab. So you generated thousands of pairs that are uniformly distributed over a square. You use this function rand in Excel, and that generates a random number between 0 and 1. Every time you use it, it generates an independent sample from a 0 to 1 distribution. So if you fill 2 columns with this, then the row in those 2 columns is going to give you 2 independent samples, both from 0 to 1, that you can view as an XY location where your marble fell when you dropped them onto this square. And then because we have this simple formula that says, well, okay, we know that if it was inside the circle, then just the x coordinate squared plus the y coordinate squared, that sum is going to be less than or equal to 1. So we have a nice, what we call predicate, to tell us if we're inside the square or inside the circle or outside the circle. So then that gives us a string of 0s and 1s, and that's what's down this C column here. And then you just count how many of 1s you get, divided by how many total rows you have, and then multiply that thing by 4, and you have an estimate of pi. So without any trigonometry, really, I mean, that you could argue that there's maybe some here, there's Pythagorean theorem or something like that, but without any crazy trig functions, without having to do any, I mean, this is similar to measuring the circumference of a circle and dividing by diameter, measuring it super precisely, but our measurements, we're effectively measuring an area, measuring 2 areas, the area of a circle and the area of the square it's inside. But we're measuring them by measuring tiny little chunks and then adding those chunks up together. And so that's kind of like, well, how precisely do we measure the area? Well, we just drop more random points, and eventually our random points fill the area. And that's like really, really precisely measuring the 2 areas. And so then our estimate of pi will be really, really precise. But we can coarsen that by measuring less. And so that's what we kind of experimented with in the lab. And so with that in mind, I forgot how many, I think I had you do 10,000 samples for pi. I'm not quite sure, but I think there was 10,000 samples. And so what you can do is you can say, well, if you asked your lab mate, like if I were to give all of you guys the lab reports for lab 3, then your question, even though you might have done the question 1 exactly the same, across say there's 31 people in the room right now, counting me. So across the 30 that are in the room right now, there would be 30 different estimates of pi. They would all be close to pi, but they wouldn't quite be right at pi. Now we could take those 30 estimates and then we could use them to calculate kind of a standard error. And that's what we're seeing here, is we're saying that, with those 30 estimates, then there's, or I could say, basically, if I took one of your estimates, I could calculate a standard error, and that standard error would represent the variation I would expect from all of your other classmates. And that's what I've plotted here. So for 10,000 samples, your standard error, which is sort of represents the variation in estimates across all the students in the class who did this experiment, then that standard error would be, say, this big. If I asked you to do fewer samples, then you would have more variation across students doing the exam or doing this test or doing this question. And then of course the standard error bars would be bigger. And then if I asked you only do 500, to be even bigger. And then on the flip side of that, if I asked you to do 10,000 or 100,000 or a million, the standard error bars would get smaller. And so when we start thinking about random sampling, we have to realize that the experiments we run are themselves a random sample. And so if you rerun experiments, you're going to get slightly different answers. And we need to somehow be able to quantify that. And so that's sort of motivating what we'll see, especially after the midterm. Now, you should remember standard error bars from 380 or 385, but you should also remember 95% confidence intervals. And we are going to talk a lot about confidence intervals in the class, and we will, if you're not familiar with what to really interpret or how to interpret confidence intervals, we'll get there. And by the end of this class, you will look at a confidence interval and you will see a t-test, because a confidence interval is a graphical visualization of a t-test. A 95% confidence interval are all of the hypotheses that a t-test could not reject at a 5% level. And so if we look at this 95% confidence interval here, we have pi. This is what we know is the true value of pi. Now, every time you did a Monte Carlo simulation and you did all of those, you averaged all those runs, you were estimating pi, but your estimates have variance to them. So we don't have 100% confidence in your estimates. So what the confidence interval is saying is that based on the values that you grabbed from your experiment, then so you had 400 samples or 4,000 samples or whatever, then we're going to take your estimate that you estimated for pi and we're going to put a confidence interval on it. And that confidence interval will be all of the hypothetical values of pi that we can't reject based on your data. And so as we see that as you take more and more samples in your Monte Carlo executions here, then that confidence interval gets tighter and tighter and tighter. And not surprisingly, it collapses around the real value of 3.141592653589793 or whatever, the double precision value. So it keeps getting smaller and smaller and smaller and smaller, but it collapses around that value. So it would be very, very rare. Well, I mean, it would be 5% rare for these confidence intervals not to include pi. But when you have few numbers of samples, they include lots and lots of other things too. So if you get a value of 3.1, then you could say, well, 3.1 is probably not the value of pi, but I can't reject it because that's my estimate. It's 3.1, but there's probably other values that I also can't reject, like 3.11, 3.09. So all of these values I could not reject with a t-test. So I'm going to bundle them into a confidence interval, and the confidence interval will be all the values that I can't reject with a t-test. And that's what we get here. So as you take more samples, you can reject more things, and that's why these confidence intervals get tighter, and that's why they collapse onto pi. So that's something that I think is, that to me is an interesting result from this lab. And I didn't ask you to do multiple, different numbers of samples, but if you were to, then you would see that your numbers, you're going to get more and more precise, and your estimates are going to get closer and closer to all of your neighbors' estimates in the lab. Okay. So before going on with that, are there any questions about what I just said there about, again, we will formally define what a standard error of the mean is and how it relates to a confidence interval and how both of those things relate to the t-test and all of that. That will come. This is just a preview of what is to come. But hopefully some of that you at least feel that you've seen a little bit of that before in, say, 380 and 385. So any questions about the data that you got from this part one? Or about my interpretation of these things?
I was kind of wondering, so do you have any reason for, so just looking at the data that you have right now, it looks like the mean for the ones with N500 is so much further, like towards 3.05 instead of 3.15. Do you have any explanation for that?
That is an excellent question. Thank you for asking a question. Yeah. So this asterisk down here, you basically what you're viewing right now is as I generated 500 rows in a spreadsheet, and then I calculated an estimate of pi. It just so happened that for that run, my estimate of pi came out to 3.05. And so then what I can use is a little bit of mathematics to then calculate based on the variance that I see across my 500 executions, how many ones I get, how many zeros I get, then it can calculate this confidence interval. And this confidence interval basically has a 95% chance of including the actual population mean. So it was my bad luck to get a low value here. I could have ran 500 runs and got a high value here. Now, my hope is if I ran that, well, what I kind of know is that if I were to get a high value for that, so like say up here, the confidence interval that I would calculate for that high value would also intersect pi. So you're just seeing the effective chance right here that this happens to be 3.05. And it does kind of look like there's this like, I don't know, it looks like it's kind of rising and then like overshooting and then ringing or something. That's just purely by chance. If I were to rerun these 500 runs, I could have gotten a larger number too, but the confidence interval, 95 out of 100 times, would still overlap pi. And so if I were to then rerun instead with 1,000 runs, I again could get a number lower or higher than real pi. But the confidence interval, again, 95 out of 100 times will include the real value of pi. Does that make sense?
Yeah, that makes sense. Thank you.
And thanks again for asking that question. And just in case it wasn't clear for everybody else, I didn't mean to imply that the standard error of the mean that I've calculated here, or the confidence intervals I calculated here, are statistics from the 30 of you. What these are meant to be is one of you calculates a value, 3.05, but then looking at the variance across all of the values you use to calculate that value, you then configure what the confidence interval are. And that confidence interval is, again, 95 out of 100 times will include that real value. And so if we were to look across all 30 or 33 now people that are in the class that ran the experiment, all of the little asterisks for all of you would be wildly everywhere. But in most of you, say 29 out of 30 of you, the confidence intervals that would be calculated from those asterisks would include pi within them. And so so you could have high, low, but hopefully the confidence interval will include that. And this is a big reason why engineers and scientists should never, ever, ever, ever report point estimates on any technical document. Interval estimates are the only way to go, because point estimates don't communicate these values here. You might see that, like, right now in the news, there's this effective reproduction number for SARS-CoV-2, or for COVID-19, and it's RT. A lot of times they talk about that, and they report point estimates in the media because people don't, they're not necessarily comfortable with interval estimates. But if you actually look, so their point estimate for Arizona right now is 1.01. But the confidence interval, the 95% confidence interval for that is something between like 0.95 and 1.06. So what that means is that they actually can't reject the hypothesis of an RT, an effective reproduction number for COVID, between 0.95 and 1.06. It might be shrinking less than 1. It might be growing greater than 1, or it might be exactly 1. They can't reject any of those. They know it's probably not 0.9 because that's outside of the interval. It's not 1.1 because that's outside of the interval, but they can't reject anything within the interval. So you never, ever, ever, ever report a point estimate, because you have no confidence in that point estimate, because that point estimate is just as likely as anything else in the confidence interval. So you should, as you go off into the professional world, always report confidence intervals. You might give a point estimate just for PR purposes, but internally, technically, you should always be looking at the interval, because the interval matters so much more than the point estimate. All right, any other questions? And I will somehow contradict myself because for the first half of this class, we pretty much only worry about point estimates, but then I'll start beating you over the head with interval estimates in the second half of the class. So that by the time you do your final project, you'll be reporting intervals coming out of your simulations and not points. So rather than saying, you know, the average time in system for these customers was 5 minutes, then you'll say the 95% confidence interval for the average time in system was between 4.5 minutes and 5.5 minutes. And that means that the real population mean was somewhere in the middle there. We don't quite know which one it is. We're not confident enough to say it's 5, but we know it's not the things outside of this interval. So we're just going to give you the interval of things that we don't really know which one it is of. So the things we're not confident in rejecting, we're going to present to you. That's what a confidence interval is. It's like kind of ironic that a confidence interval are things you're not confident about. All right, great. All right, so let's then march on here. So the practical lesson, aside from all of the like the statistics stuff and the Monte Carlo stuff, the practical like what can I use in my everyday, you know, Excel usage or Google Sheets usage is that if you need a random number between 0 and 1, rand is the function that you'd use, you get that from. So it's sort of a magic thing you get from Excel is rand. And in the next lecture, in the next homework, then we talk about how you build rand, because it's really, really important in this class to have access to random numbers. So we have to then say, well, then where the heck do you get the random numbers to begin with? A computer is deterministic. Well, we will talk about that in the next lecture. But Excel's already done it for you, Microsoft has implemented it for you, and there's this rand function, and that's how you get a random number between 0 and 1. So that's kind of our first kind of practical lesson. Okay, so then the second part of that lab that I want to talk a little bit about was this activity network stuff. So in this stochastic activity network, we had these 3 activities that were operating in parallel. One of them has a 3-part activity where each individual part was between 2 and 4 minutes. The other one was a 2-part activity where each individual part was between 3 and 6 minutes. The other one was just 1 part between 6 and 12 minutes. All 3 activities have the same average completion time, 9 minutes. And so the question is if you have to wait for all 3 of them to finish in order for the whole activity to be finished, then what are the statistics of the whole activity's time? And a Monte Carlo run or a simulation is great for this. So in the Monte Carlo simulation, kind of similar to our pi example, each row is sort of a sample. And so in those rows, we've got a 3-part duration here. So I kind of compressed things together and I just said, well, I just took a sum of 3 random variables. So this is like equals rand plus rand plus rand. And then there's a 2-part, which is like equals rand plus rand, and then a 1-part, which is like equals rand. Now, we had to use a special formula that we'll talk about in a second to scale our random numbers. So instead of being from 0 to 1, they were from, say, 2 to 4, or from 3 to 6, or 6 to 12. But then we can put them all in this little formula here. And then once we know the duration in each row of each parallel activity, then we can just take a max of those. And we can say this is the length of the total activity. And then we can say, just to find out who were we waiting on, then we can ask Excel to say, all right, which one of these 3 total durations matches the total duration? And then that gives us the ability to do a sort of a histogram of seeing who takes the longest. So, so that's, you know, our idealized spreadsheet for this. And the results that come out of that look a little bit like this. And so I've got a distribution of total durations up here. And then I hope you can see here that although the individual paths mean were all 9 minutes, the total that has to wait for all of them actually has a mean somewhere above, well, in this case, it was about 10.2. So I gave you a point estimate here. I should have done a confidence interval, right? Because you're going to say, wait, no, my estimate was 10.1, and somebody else can say my estimate was 10.25. And so we could all argue about our point estimates, when in the end, what I should have said is, well, my 95% confidence interval was between whatever, 10 and 10.8. And you might have a different confidence interval than me, but all that I'm really communicating there is I can't reject any average in between 10 and 10.8, but I definitely can reject 9. The average was not 9. So that's what I should have done. But I didn't do a confidence interval here because I didn't ask you for confidence interval, just asked you for an average. And the average for this is definitely much larger than 9. So this activity is taking much longer than 9 minutes. And if I look at my critical path distribution, then you might have expected a 33 to 33 to 33% sort of split, where the top pathway is longest the most, only a third of the time, the mid a third of the time, and the bottom one only a third of the time. Or you might have expected the one where you're adding up times, maybe that takes the longest. But interestingly enough, the one where you're adding times is more often the shortest one, or I'd say it's least often the longest. And the one where you're just drawing a random number between 6 and 12, that's the one that more frequently is the one driving the total activity time, taking the longest. In order for us to understand that, so I think this was me, I did another sample. So if I were to rerun this experiment again, so this is just, it shows that these results are typical. And so, oh, I'm sorry. So I ran this with 500 samples. This one's with 1,000 samples. So I'm kind of, fine tuning that. And so I see even with 100,000 samples, then I see that this is not a numerical error. It really is the case that the distribution of durations looks like this, which is well above 9 minutes in the average, and that the third path, the path where it's just one activity, takes the longest most of the time. And in order to understand that, what we can do is look at the distribution of times along the top, middle, and bottom paths. And what we see is that along the top path, where it's 3 uniforms added together, then there's a private question in the chat, which I'll answer here in just a second. With the top one here, where we've got 3 small activities added together, then it looks much more bell-shaped. In the middle one, where you have 2 small activities added together, it looks like a triangle. And in the bottom one, where you just have 1 activity, well, it looks like exactly what we expected that activity to be. And as a consequence of that, then it is very rare for the top branch to take long. It pretty much clusters around the average. The top branch, when you're adding 3 shorter activities together, whose means all add up to 9, is much more likely to have a 9-minute mean. The middle one, still, it's less likely, but it's maybe a little more likely than the top branch, but still in the middle one, you still get a cluster around the mean of 9. You don't get things that take a very long amount of time. If you think about it, both of those things, that should make a little bit of sense, because how the heck could you get, let's say, 12 out of here? In order for you to get 12, that requires you to get 4 plus 4 plus 4. In other words, the top activity is 3 independent random activities. In order for the sum of those 3 independent random activities to be the longest, to be 12, and that requires each activity to sort of be in the unlucky state of taking the longest itself. And it's just going to be very, very rare that if you add up 3 activities, that all 3 of them will end up taking the longest amount of time. It's going to be sometimes it'll be pretty likely to have the first one take a long time, the second one to take an extremely short time, and the third one to maybe take some intermediate time. So that's the reason why, as you start adding things up together, you end up basically making, you add a level of independence to the execution where it sort of prevents these extreme events can happen, because these extreme events mean extremely unlucky, because every one of your independent subparts would have to also be in an extreme case. And that's just not going to happen very often. It's going to happen a little more likely in this middle case because you only have 2 to worry about. So yeah, every once in a while, the one activity is going to take really long and the second activity is going to take really long. That's going to happen more often in the second, in this case, than this top case. But it still doesn't happen as much as in the top case, so it happens more often here that you can get unlucky twice. In this bottom case, you just have the uniform distribution. So here, the bottom case, by saying that there's no sum, it's just a uniform distribution, we're basically saying yeah, you can get unlucky, you can take a long amount of time, but by saying it's a uniform distribution, we're saying it's just as likely for you to be in the really bad case of taking a long amount of time as it is to being in the really good case of being a very short amount of time. So summations create unlikeliness in tails of distributions. And that's the fundamental reason why the central limit theorem works. And so you've learned about the central limit theorem, which said as you add up a bunch of independent random variables, their sum becomes more bell-shaped. Now you're seeing that by simulating it. By simulating summing up 3 independent random variables, you're seeing that the reason why things become more bell-shaped is that in order for things to live in the tail, then you have to be unlucky enough to get a tail result in each of your independent things that you're adding up together. And that's just going to be, it's like, you know, it's like winning the lottery 3 times. Is that in the activity that has 3 parts, that's like having 3 lottery tickets. And so if you were to end up taking a really long time in that activity, it's because you took a really long time in all 3 independent activities, and that's just super rare. So that's why the central limit theorem works. And because of this, then when you put in parallel a group of activities, even if they have the same average, if one of those parallel branches is the sum of a bunch of activities, it will most likely finish sooner than things that have less summation going on, because the variance will be more compressed with the summation, if you can guarantee that the average across all the branches is the same. So there was a question in the chat related to this where you say, so could we say that doing small activities is usually better than doing one long activity? Well, I guess it just kind of depends on what you mean by better. But statistically, what I can tell you is that if the averages for the total activity are the same, and when you sum the activities up together, they're independent. And by independent, I mean there's no relationship in the result of one sub-activity and the result of another sub-activity. Then you will get less variance in the sum than you will in the individual because of this like winning the lottery multiple times property. And that's kind of the fundamental property that's embedded within the central limit theorem. And the other thing I'm trying to show here is that the central limit theorem works even for a small number of summons, of things that you're summing up. So even though I've only added up 3, this already looks bell-shaped. If I were to put a real bell curve on there, real normal, this would not, I mean, this is not matching up with a normal, but it still looks pretty bell-shaped and it looks pretty darn symmetric, and that's pretty cool. So are there any questions about that? About the, you know, the reason why we get this extra time taken for the part that doesn't have sums, or an intuitive feeling for where the central limit theorem comes from. And later on, when we start talking about input modeling, then you should think back on this, because whenever you have additive processes that you're trying to model, like you're trying to model how long it takes someone to assemble a part. And if you look at the recipe for assembling a part and it says, well, they got to do this, and then they got to do this, and then they got to do this other thing, then you look at that and you could model each of, and I'll get to that question in a second, you could model each independent thing in the recipe as a separate input model. But if you notice that they're always completing them in sequence, and you notice that the success in one is independent of the success in the others, then sometimes you just model the whole process, the whole recipe, as a normal distribution. And that's because of the central limit theorem. Because why bother with coming up with some crazy distribution for how long it takes to screw a screw in, where if you have to put 100 screws in, just, you know, take the average and the standard deviation for how long it takes to do a couple screws in, and it's going to be a bell curve. So there's a question, why is the average duration over 9 again? So the basic idea here is, if you buy my argument that that this is the distribution for the top activity branch, and this is the distribution for the middle activity branch, and this is the distribution for the bottom activity branch, then the reason that the average for the max, basically we're saying, well, what is the distribution of the max of these three distributions. And the idea here is that because this uniform it's very likely to take a long time in the uniform distribution, but it is very unlikely to take a long time in this distribution up here. And so when we look at, so you can imagine if we think of all three, let's say you get lucky in the top branch and it happens to finish pretty quickly. Let's say it's 7 minutes. Well, that's not going to end up counting because it gets masked out by everything else. And so this 7 minute long duration, well, when I take a maximum, well, both of these are more likely to be longer than 7 minutes. And this one, this uniform, is really likely to take longer than 7 minutes. So already the process of taking a max is necessarily going to shift the mean. So if you take the max of a, and so there's a question, isn't it just as likely to take a shorter time? It's true that the uniform distribution is just as likely to take a shorter time than a longer time. But if we're thinking about what takes the maximum, then you could say, well, what does it take for the average maximum to be 9? Well, that means that some of the maximums have to be less than 9. Well, how do you get some of the maximums less than 9? Well, that means that all three paths have to be less than 9. They're going to get a 7 here, a 7 here, and a 7 here. And what we're sort of seeing here across these three branches is like that in itself is going to be very, very unlikely, because if you're lucky enough on 2 of these distributions to get a low number, then the other distribution, because it's drawn independently, may itself get a high number. And what's even worse is that this uniform distribution is just tossing numbers everywhere. And so if you happen to get lucky enough to get a low number on the top branch and a low number on the middle branch, there's a huge probability that the number you get from the branch below is going to be above 9, let alone above the number that you drew. And then, so there's another private question here. So colloquially, if there is less summation, then that path is likely to be the critical path because there's more probability for the times to be larger. Yes, yes, that's a great way to put that, is so there's kind of 2 questions here. Why is the average duration of the total activity greater than 9? In some ways, that's just a product of us taking a maximum. If you take a maximum, then that means that even if some of the things you're taking a max of are lucky enough to be low, you have to them all to be low for the maximum to be low, and that's just unlikely. But then adding to that, the reason why the 3rd branch is most likely to take the longest is because it is scattered all over the distributions. It's sometimes short and it's sometimes long. There is much, much more a chance for the 3rd branch to take 12 minutes. It's nearly impossible for either the other 2 branches to take 12 minutes. So right there, that kind of just tells you that the fact that there is a significant probability of the 3rd branch taking 12 minutes tells you that, well, you know, it's probably going to dominate in terms of these other ones. Yeah, it's sometimes going to take shorter. And I mean, it's got a high probability of also taking 6 minutes. And so it will sometimes be the shorter distribution. And that's what kind of is going on in these other 2. But if we're really caring about how often is a branch the longest, then the uniform, I would put my money, if I had to put money on it, if I had to just pick one time who's going to take the longest, it would sort of be a dumb idea for me to say that the 1st branch is going to take the longest. If I only got one shot at this, I better put my money on the uniform distribution because it puts a significant amount of its mass up here on long durations. If I put it up on the uniform distribution, I'm sort of counting on this tail working out. And although sometimes the top branch takes a long time, it's pretty rare that it takes a long time. Any other questions about that? And the reason I am taking the time to go over this kind of detailed thing is not just because it's kind of cool to sort of understand where these distributions come from, but I'm hoping you're seeing that, like, this distribution that you see out here, I'm hoping that that is not a distribution that you recognize from, say, 470 or 380 or 385. I'm hoping you're seeing that the complexities of how you get to this top distribution, or how you combine all these distributions together, or how you come up with all of this, these are not nice and tidy forms that are easy to solve on the back of an envelope with with a pencil and paper. These may require a deeper level of analysis that may not be mathematically tractable. And that's part of the reasons why we're doing simulation. If we don't know really what math to put down, but we can build a system that accurately puts these parts together, and then we can take statistics on the outputs of that system, then we can analyze those statistics qualitatively if worse comes to worse, if we don't necessarily have a more quantitative way to do it, and make sense of it. So simulation gives us access to distributions that are maybe sometimes out of the reach of the basic mathematics that you learn in classes like 470, 380, and 385. All right, any other questions about these results? All right. So hopefully the way everyone built this thing was like I said, in that spreadsheet that I kind of talked about here. And you could, in order to count up, how often things were the critical path, you could have used tools like frequency, average, COUNTIF. You could have used the histogram tool in Excel. So hopefully you had a chance to play with some of that. The practical lesson that I want you to take out of this, aside from all the stats stuff, is that we already know how to generate a random number in Excel or Google Sheets from 0 to 1. Now, how do we generate a uniformly distributed random number between any A and any B that's greater than A? And we learned this simple little formula here, where you just take the range and you scale up the 0 to 1, and then you shift that range over by the minimum value. And that is a simple way that we can convert one type of randomness into another. And so we took a randomness where we take a random outcome from 0 to 1, and we use a mathematical expression to turn it into randomness between A and B. And this is kind of thinking ahead to some of the things that we're going to do before the midterm in Unit C and Unit D in particular, where we are going to figure out how to build more exotic mathematical formulas, where we take that same 0 to 1 and we turn them into an exponential distribution, a Weibull distribution, et cetera, et cetera. So this general idea of using a formula to turn 0 to 1 into whatever distribution we want is a powerful thing that we will use throughout the rest of the semester, and is what is used behind the scenes when you ask Excel for, say, an exponential random number or a normally distributed random number, and so on and so forth. So this is just the tip of that iceberg. And so I might skip some of the rest of these things here, but I did at least add the last couple of slides that I put in this presentation, which I'm going to sort of jump ahead here, is that sometimes you're not going to want to draw continuous outcomes, like between 0 and 1. Instead, sometimes you're going to want to draw discrete outcomes, like you're going to simulate a 6-sided die. You're going to want to say, well, I want the number of dots on that die to come up in a way that represents the same way a 6-sided die would. So I want a uniform distribution across the numbers 1 through 6, but I don't want 1.1. I just want all of the whole numbers 1, 2, 3, 4, 5, and 6. Or maybe you want a biased distribution where 6 comes out more often than 1, or so on like that. And this would be very useful for, say, the muffin simulation, where we have a random number of muffins that arrives every day. And we want to say, well, how do we generate that discrete number of muffins every day? Do we just draw a continuous number and then round it? And if we did, what would the distribution that came out of that be? And so what we'll learn how to do as we move on here is you can take any probability mass function like this one out here, which has 3 outcomes, and it says 20% comes out 1, 50% comes out 2, and 30% comes out 3. And if I take any one of those, and this is just what's kind of summarized on this, if you turn that into the cumulative distribution function, which you should remember from 380, 385, which just represents the probability that an outcome is less than or equal to that outcome. So for outcome 1, it's also 20%, but for outcome 2, it's the sum of these two together, it's 70%. And then for outcome 3, it's the sum of all of these together, which is 100%. that cumulative distribution function gives you a rule that allows you to turn a continuous random variable between 0 and 1 into this discrete random variable. And you do that just by drawing a single number between 0 and 1, and then asking where it falls in the CDF. And so if it falls between 0 and 0.2, you give an outcome 1. If it falls between 0.2 and 0.7, you give an outcome 2. If it falls between 0.7 and 1, you give an outcome 3. And so with a few little if-then statements inside an Excel spreadsheet, you can now generate a discrete random variable with any probability mass function that you want. And so, and again, it's using this magic of turning a continuous random variable uniformly distributed between 0 and 1 into another random variable. So all of our randomness kind of is given birth to by the uniform distribution between 0 and 1. And for Unit C, we're going to learn all the tricks for how to turn that randomness from 0 to 1 into any randomness that we want. That's kind of where we're heading in Unit C. All right. So if you're interested in more of that, then you can look ahead in these slides, which are online, and I kind of give an Excel example of how to do that. And then in Unit C, we're going to learn about the inverse transform technique, which you can read ahead in Chapter 8 of the book, and it's also the subject of homework D2, which I'll have posted soon. And that's all that I want to talk about for the lab. So we otherwise have kind of a short lecture today about agent-based modeling in NetLogo. So are there any questions about that, about the lab, or any other reflections about the lab? And again, I mentioned before, because a lot of people don't understand what industrial engineering is, including industrial engineers, but it's even worse for those who aren't industrial engineers, right? And I've mentioned that industrial engineers, you know, are kind of this weird blend of science and scientists and engineers, and they have to use statistics in a more rigorous way than all the other engineers. The other engineers pretend like they know statistics, but they still deal in point estimates and things like that. And as an example of that, my background is, and I saw that question in a second, is in electrical engineering. That's what I got my bachelor's, my master's, my PhD was all in electrical engineering. And the inverse transform technique was something that I didn't learn until an upper level, graduate level course in stochastic processes in my electrical engineering curriculum. And you were learning it here in your senior year. And it blew my mind as a grad student when I was in electrical engineering, the inverse transform technique. But it is just going to be commonplace in this sort of undergraduate thing here. So it just goes to show that like we really dial up the probability and the statistics here in IE, and that's why you should really view that as one of your strengths, is your ability to handle models, probability, and statistics. That is like your bread and butter as an industrial engineer. Okay, so the question was, so would we expect the total distribution of duration to be reversed if we used a min function? That's a really excellent and interesting question. And I would have to think about that more. I am hesitant to say exactly that because max and min seem symmetric, but it turns out that if you actually write out if you do something, there are some distributions where you can actually write out the mathematics of what the distribution will be if you take the min of other known distributions. And mins and maxes end up turning out being very different. And so, especially for exponentials and things like that. So I'm not confident that you would have just like a flipped version of that for the min distribution. I don't know what the shape would be. I think if I sat and thought about it for 5 or 10 minutes, I probably could at least have a good guess of it. But that's what I would encourage you to try, is that you can do this right now. So you know how to take histograms or these sort of distributions. Just take your Lab 3 homework and flip it and just take the mins instead of the maxes and see what you get. And that's the beauty of simulation. It's like a lot of times you're like, I think I can reason through this mathematically, but I kind of need an appetizer to get me going. And that appetizer is very often just do the sim. You do the sim, you take the stats, and then sometimes the shapes speak to you and you say, wow, you know, I didn't expect that to be bell-shaped or that to be, you know, square-shaped or whatever. And then that often tells you kind of the next step to do when you might have gotten stuck in like the mathematical derivation that you're working out. So definitely encourage you to try that experiment. It is my suspicion that it won't be like a symmetric reversal, but it will be something that you'll need a kind of a similar type of analysis technique where you have to kind of think about like, well, you know, if this one was the max, and what's the likelihood that these other two will be the max, and so on and so forth. So I don't say reversed, but similar. All right, any other questions? Great. All right, so let's do an attendance exercise question. And this, also I'll put this in the chat here. And the question I'm going to ask is, what do the letters CLT represent? So just sort of burning this thing into your mind, this CLT. So I talked about it, and it's the thing that has to do with this, if you sum up random variables, their sum tends to look like a bell curve if they're independently distributed. So I just want you guys to always have the central limit theorem in your mind. All right, and with that, let's get on to the main business of the day, which is introducing you to agent-based modeling, which I use a lot in my own research. And so, just a couple of reminders and announcements, and that Homework B solutions are available on Canvas. The grader tells me that he's graded the main assignment. And for those of you doing the extra credit, so he has divided up, so he graded all of the main ones first to get grades out there, and then he's going back and he's grading all the extra credit. So if you say, hey, wait, I thought I did the extra credit right, you didn't get the right points, just wait a bit, and I think he'll start crediting the extra credit ones. So, but at least you have the main points there. There's interactive Canvas activity coming up. Again, the drop policy is like 7, and I'm saying there's like 15, but I think there's only like 11 in the semester. So I mean, you only end up having to do 3 or 4 of these things. So again, I think it's great if you do all of them, if I prefer that you do all of them, but don't feel like I'm forcing you to do all of them. They're really just meant there for you to have the opportunity to do more frequent practice than the homeworks. Speaking of homeworks, Homework C2 has been available and it is due next week. You're gonna have to do a little bit of reading ahead. And the reason I've accelerated this homework is to give us time to get homework D out there, because you need practice on both random number generation and random variate generation before the midterm. And so the midterm will be coming up. The date is on Canvas. Don't fret, it's not super soon. It's like 2 homeworks away. But basically, it's going to be like this homework is due in a week, and then the next homework will be assigned, and it's due in a week, and then there's a couple of days left over there to allow late submissions to come in and the homework solutions to be released. And then we'll have a midterm review session, and then we'll have the midterm, and then you'll have an opportunity to do a midterm retake a week after that. So, so that's kind of what's coming up there. So look ahead for those assignments. Also, again, I'm not going to spend a lot of time on this, but the competitions are out there. If you want to do the competitions for your final project, I believe most competitions have got a registration deadline at the end of this month, so you have to get on that. So any questions? All right, I'm just going to skip ahead here to say, I just want to kind of, most of the NetLogo stuff you'll get actually in Lab 4's video. So I go kind of in detail on how to work with NetLogo there. Today, I just want to at least motivate why we're even talking about NetLogo. So most of this class is about discrete event system simulation. It's process-centric. There was this nice article back in 2015 in Operations Research Management Science Today, ORMS Today. And I've linked to this on Canvas if you'd like to read more about it. And it's talking about a survey of discrete event system simulation models and software tools and application spaces. And so if you're wondering where can you use the tools that you learn in this class, read this article. It talks a bunch of great examples: parts, patients, vehicles, wide divergent range of manufacturing, healthcare, and other service settings, logistics, transportation, military, just a few. If you're looking for ideas on what to work on for your final project, this is also a great resource to take a look at. So put that there. So discrete event system simulation is great. So then why do we bother with these other frameworks? So I've mentioned before that there's agent-based modeling, there's discrete event system, and there's system dynamics modeling. So they basically fall on a different level or a different point in the modeling continuum. And so when we ask these what if questions, then the tools that we use to help answer these what if questions, these models, can either be very tethered to our system, very detail oriented, in which case their answers are not very generalizable. They're very specific to that system. And that's what I refer to as being analog. So they have realistic detail and scaling, or they can be metaphorical. So they can be very generalizable. And those very generalizable models may not have enough detail to sort of be customized for or optimized for your particular scenario, but they give you some lesson which can apply across a wide range of scenarios. And so they're a little coarser grained, but but it's not necessarily that they're worse. They have a different focus. Like, you're not asking a general question when you choose one of these models over here on analog, but you're asking a more general question when you choose one of these more metaphorical models. And discrete event system simulation is kind of in the middle. They're meant to be illustrative, so they don't capture all of the details of the real world, but they capture enough details to give us variation that looks realistic. But they still allow us to ask questions that are not necessarily specific to all of the weird details of a particular factory or particular store. There's hopefully lessons that we can generalize across factories, across stores, and so on. So DES is what we talk about for the rest of the semester. What about these other two? So on the metaphorical side, we have system dynamics modeling. So this is the type of modeling that is handled in IEE 477. And so I've already introduced these a little bit back in lecture A2. These are models which are basically coarse-grained mathematical models that are just put in a graphical framework. So you can write ordinary differential equations like this one down here, where your state variable is called a stock, and the right-hand side of the differential equation is called a flow. And instead of writing this equation, you draw this diagram and you wire things up together, which show relationships between these differential equations. And then when you hit go on the simulation, what it's actually doing is solving a differential equation. It's integrating the differential equation to show you how these stocks behave over time. So this kind of mathematical approach is great for coarser grained, highly generalizable questions. So this is very topical. So people talk about the spread of disease right now. So you may have heard about SIR models, susceptible, infectious, recovered models. And these SIR models are one of the best kind of examples of system dynamics models. And so in this case, we have 3 stocks. We have a number of people are susceptible disease, a number of people are currently infectious and are shedding disease, and a number of people are recovered. So they've had the disease and they are not infectious anymore. And we are keeping count of how many people are in these 3 groups, but we don't keep track of any other details. We don't know where they live. We don't know how they're moving around. All of those details are not there. And so it is a very, what we say, coarse-grained view of the system, and it represents general trends that are generalizable across, say, diseases. You may have heard about the R0 number or the RT number, the basic reproduction number, and the effective reproduction number, which represent how diseases spread. And what people found is they built these SIR models, and they found that there is this generalizable concept of the basic reproduction number, that if you know that number for a disease, you know a great deal about how that disease will spread. And that R0 number can be applied to a wide range of diseases. So that's what I mean by a generalizable insight. It's not tailored. It's like something that you get the lesson once and then you have to relearn it for something totally different. You just adjust your R0 and then all the other lessons follow. And so a system dynamics model is often drawn like this. This is one that I drew in a program called VinSim, that you draw these populations and you connect them together. And what you're just doing is graphically representing a differential equation that just does the bookkeeping of how many people are susceptible, infected, and recovered in a population without knowing the details about how they're bumping into each other. And that's a system dynamics model. What we're focusing on in lab are on the other end of the spectrum. And those are these agent-based models. And these do focus on the interactions between individuals and how all of the complexities of their surrounding environment can get in the way of the insights that we might get from a system dynamics model. So a system dynamics model says it's all about R naught. But somebody says, well, it's not actually all about R naught, because if you quarantine a bunch of people, or if you do with all, if they add in all of these ifs, like if you did this and this and this other thing, then maybe you could shape how the disease spreads in a way that is not how the mathematical model suggests. And then somebody says, well, how do you build a mathematical model to predict what's going to happen? You say, I have no idea, because that mathematical model would be too difficult for me to build. So instead, I build a simulation. And so these agent-based models often look something like this, where you've got sort of a representation of a virtual world where agents are moving around in that virtual world, and you've got ways to interact with that virtual world in order to change their properties. And then you've got output statistics that come out of that virtual world that are measurements of how things are going in that virtual world. And then you can test whether or not, say, disease spreads in a way that you might expect from the basic mathematical model, or if the complication you've implemented changes things drastically from what the mathematical model predicts. So that's kind of the things that we can do in an agent-based model. These historically were used by biologists and social scientists to try to wrap their heads around ecosystems and social systems, where there were a bunch of interacting parts, where you could kind of view things at a coarse-grained scale and say, well, I think I generally see that something's happening, but I don't know why it's happening. So to test hypotheses on what's going on at the micrograin level, then you could come up with these sort of ideas of how you think people bump into each other, and then allow them to bump into each other, then see if the coarse-grained perspective of your simulated world matches the coarse-grained perspective you see in reality. And if it does, then you might be able to play around with your virtual world as a way to better understand what's going on in the real system. And so, you know, birds and fish and ecosystem interactions and so on were kind of sort of, you know, where these things were first used. Engineers picked up on them, and so in engineering, we often refer to them as multi-agent systems, or we will use agent-based modeling simulations to capture multi-agent systems. And these are things that people worry about, you know, multi-robot systems, multiple drones in a battlefield. How do they interact with each other when you scale up the numbers? And these are the types of things you often see simulated in these simulators. And so we will be using this program NetLogo in Lab 4. And, but there's a bunch of other options here. If you take 477, you'll use AnyLogic, and AnyLogic itself can do agent-based modeling. So NetLogo is not the be-all and end-all, but it is very popular in the agent-based modeling community. But if you look at commercial platforms like Altriva and so on, then these are much more expensive programs. NetLogo is free, but they have like a much tighter and nicer looking graphical front end, which might be more appealing to some of your stakeholders. Are there any questions about the motivations before I just kind of cover the basic overview of the stuff that I'm hoping will help you as you move into Lab 4? So the basic ideas, I have questions about what are the differences between the discrete event systems, the system dynamics modeling, and the agent-based models. All right. So we've learned about entities in discrete event system simulations. The entities in an agent-based model are the so-called agents. These are things that interact with each other. So they are not shuttled around processes. They have their own rules for what they do in the next time step. Do they move? Do they stay put? What happens if they had just bumped into another entity? You have all these rules which are conditioned on what just happened. And so they can be very event-based. As a consequence, sometimes for speed underneath the scenes, people will implement agent-based models using discrete event system simulation. So there will be an event calendar, but that sort of means that you kind of are able to predict when the next time two agents intersect are going to be. And sometimes that's hard to do. So it's more common for things to sort of, you simulate a tiny little fraction of time and you move everybody independently in that tiny fraction of time, and then see if after moving them independently in that tiny fraction of time, two agents that weren't interacting are now interacting, and then run their interaction rules. That's the more common way to do it, but you can implement them with the irregular jumps that we're becoming familiar with in discrete event system simulations. Because there's all of these details on how to get all of these agents moving together, then if you move from one program like NetLogo to another program, like let's say you implement an agent-based model in MATLAB, you might think you're building the same model, but the software behind the scenes might animate your agents slightly differently. So you might move all of the agents forward all at once and then ask, do we have an interaction? But another program might move an agent forward, see if it has an interaction with an agent, move another agent forward, see if it has an interaction. So in that case, the agents they move and then interact potentially with an agent in kind of their old state. So, and there are arguments for why you might want to do one over the other. And if your time steps are not super small, if they're kind of large, you can get significant differences in your simulation based on these choices. So that's one of the downsides of these agent-based models, is you have to be much more careful about the kind of scheduling of how these agents work. Whereas in a discrete event system simulation, we kind of know exactly what the timing is going to be. And that's the reason you can do a hand simulation without a lot of extra instruction from me. Every hand simulation is going to look exactly the same. With an agent-based model, I have to tell you a lot more about how the agents are scheduled in order for you to hand simulate that model. So that's something that kind of to look out for. And what I've had students do this on honors theses before, is you can actually, once you've built an agent-based model, you can use it to calibrate other models or test other models. So you might say, I think my discrete event system simulation of the bank has taken into account all of the, I think I've properly modeled any details that might relate to sort of how cramped things are inside the bank, but I'm not quite sure. So you could build an agent-based model of a cramped bank and see if the statistics that come out of your agent-based model are consistent with the statistics you're modeling in your input models for your discrete event system simulation. So it is definitely sometimes possible to mix these two, where you use the kind of slower agent-based model to build up confidence in the probabilistic models you're going to use inside the discrete event system simulation. So they can interconnect. But usually we view them as sort of a totally different way to model systems, to ask different types of questions. And I just want to motivate that with sorry, that was a scroll wheel issue, with a competition that came out not that long ago. And I've got an article on Canvas that you can read about with this. There was a group, LMI, that does consulting work for NASA. And NASA was interested in questions about how commercial airlines would respond to potential policy scenarios about let's say, about how planes are allocated to the air. And so they wanted to know about these things, and NASA sort of felt that agent-based modeling was the best framework to answer these questions. But these are basically operations research questions that NASA was asking. So this consulting firm that worked with NASA, that used the agent-based models, apparently, and you read the article, got frustrated that they kept taking interns from industrial engineering programs and operations research programs. And those interns would have experience with discrete event system simulation, but they didn't have any experience agent-based modeling. And they'd have to end up training them on agent-based modeling tools during their internship. And it would take so long that they'd end up not being able to do anything useful during their internship. And so what they did is they built an agent-based modeling simulation competition that was meant to motivate students to learn agent-based modeling before they would go into these internships. So it was their active way of trying to get this kind of this newer simulation modality into the supply chain that goes into kind of like operations research education. And what they came up with was kind of this fun thing. They built it in NetLogo, and it was a competition where teams had to build the optimal way for people to escape a building during a zombie apocalypse. And so the idea was that you would come up with rules for, what do I do when I see a zombie? Or what do I do when I come by a room? Do I hide in the room? Do I keep moving to the room? You come with all these rules that individual agents would do as they're moving through a building. And you didn't know what the building layout was ahead of time. And then they could give you a building layout the day of the competition, and you would deploy 100 of your people with their rules. And then they could then study across the teams who had the best survivorship of the zombie apocalypse. And so everybody then was tossed into the same simulated floor plan with the same behaviors of the simulated zombies. And if you run it for whatever, I don't know, 30 days, simulated days, then you get to see how many people survive. And the team with the most number of survivors won the competition. So I thought that was kind of a clever way of introducing agent-based modeling in a nice competition framework that was kind of fun, that is still being used, from what I understand, at RIT in their operations research department. And I think at least initially had sponsorship by both Informs and IISC. So these things are really out there. And I've chatted with people at Southwest who use agent-based modeling to do airline decisions. So how do you board people on planes? How do you schedule cargo onto planes, and so on and so forth? And I think there's some really cool examples of that I'd be happy to talk about with people sort of offline. So agent-based modeling is being used out there. It is less traditional, for whatever reason, to be incorporated into these kind of industrial engineering educational contexts. So because we're kind of just still stuck on getting you up and running with discrete event system simulation. But I felt it was important you at least see it. And that's why in Lab 4, you're going to be playing with NetLogo and agent-based modeling. And I give a lot more details on Lab 4. So I'm not going to give sort of a tutorial in NetLogo here, but I've sort of given that in Lab 4. And I also have kind of a mini tutorial aside from the Lab 4 notes that's online that you can watch if you'd like kind of some more help in getting started with NetLogo. So that's kind of my background and motivation for Lab 4. And so we've only got about 2 minutes left, so we'll wrap up here. Are there any questions about any of that stuff before we close out? And I don't know if you can see it, but I happened to bring up just a NetLogo example of a virus model. And it's just sort of an example that if in NetLogo, this is an example of, instead of with this kind of, you can see sort of the effective space and how people move around. And this, this is, I'm not going to go into the details of what's going on here, but it just kind of goes to show that this is an alternative way to follow diseases through a population. It's just to have individuals move around. And if they bump into each other, then there's some probability that they get a disease from an infected person. And then you can study the statistics of how many people have that disease. That is a very different way of modeling disease spread, but the stats that you get out of it are going to look very similar to mathematical models that formally model this. And where they differ is usually where there's really interesting things you can zoom in on to make policy changes. All right, so if there are no other questions, then let's close out with last attendance questions. So again, I'll put the URL in the chat. It's also on the screen. And so a question I have for you is in, I don't know, 2 words or whatever, can you summarize the background scenario that LMI used in the competition that they gave industrial engineering students to encourage them to learn agent-based modeling, like the agent-based modeling they were using to model NASA? So what was the scenario that LMI used for their agent-based modeling competition for industrial engineering students? So it wasn't, I guess it technically was related to healthcare, but it wasn't something like healthcare or manufacturing. It was something a little more colorful. So I can put that question in the chat. What was the scenario used in the ABM competition put together by LMI and sponsored by Informs and IISC? And that's all I have for you today. I'm happy to stick around for a minute or two if there's questions. Otherwise, you can feel free to head out. And we start a new unit on Thursday, random number generation.
Thank you.
Thanks. All right, looks like everybody is trickling out. Thanks for all your questions today as well. They're really excellent questions. I was really happy with those. All right, looks like that's about it. So I will end the meeting and see everyone on Thursday.